First, I want to thank you guys for the opportunity to present this chapter. Uh, I've been following several of their chapters, and it's been a pleasure to participate. And so I'm really happy to contribute. It's a tall order to talk about asynchronous programming in Rust in 45 to an hour, 45 minutes to an hour. So I'll try to do my best. So let's start. So I'm going to, so these are the main topics that we are going to talk, like following Jon's book. Uh, it's really, he goes deep on many topics, and many of those are would need quite a lot more pages to really explain what's happening there. So it's really, the book is really intended for intermediate to advanced users there. And so I try to do my best to clear up some of the concepts, bringing some of my explanations along as well. And so Jon starts by talking about the difference between synchronous and asynchronous programming. So we're going to start there. And then we are going to see how the async await syntax in Rust is turned behind the scenes into a state machine. And we are going to need why we need pinning and what pinning is. And then we are going to talk all about reactors and waking up and going to sleep. Right. So asynchronous. So Jon starts explaining the difference here. And so I like to go to the root of words to understand them. Sometimes this is helpful. And so you see that synchronous comes from the Greek for the word sun and chronos, which is time. And so you can imagine that that refers to a process that is orderly, regular. And in particular, in programming, we say that it's not interleaving. So you don't do two things by stopping midway and picking up another thing. And so what is asynchronous? Asynchronous in Greek, the A is the negation of what follows the A. And so asynchronous is the negation of synchronous. And so it's something that is out of order, irregular, and with interleaving. And I like to use this opening example to clear up one doubt, one point of doubt that always comes up when talking about concurrency and parallelism. And so we are going to use this laundromat example. And so let's say you have you want to do laundry, and you have, let's think for now that you have one washing machine, and you also have one dryer. But you have too much load. You cannot wash all clothes at once. Like you cannot fit it into the washing machine at once, and neither can you do that in the dryer. And so we are going to do this synchronously, and then we are going to compare later how to do it asynchronously. So synchronously, we would wash the first load and wait. Like you can think that you yourself is the thread that is distributing the work. And so you put the load in the wash and you wait. When it's done, you dry, you put in the dryer and dry, and you wait. And then you wash again the second load, and then you dry again the second load, and then you are done. You can see that during part of this process, the washing machine was idle, doing no work. So that's how, so let's compare the concurrent approach, which is we're going to wash the first load, and then when it's done, we are going to move it to the dryer, but simultaneously, we are going to pick up the rest of the load and put it on the washing machine. This way, we have both the washing machine and dryer doing work at the same time. Well, in this case, at the same time, but also the task is being done concurrently. We didn't stop until the dryer was ready to put the load into the washing machine. And this is really easy to visualize with this plot. You can see the synchronous bit where the dryer, you start with the washer and then the dryer, then when it stops, washer again, and then the dryer again. Whereas with the asynchronous version, the concurrent version, you can have the washer going almost no stop as long as there is laundry to do. Okay, so how does this relate to actual examples of software? Like we can think of database calls, network calls, disk call, write calls to the disk, and waiting for a callback from your C program. Like you can think many ways in which your software is your program is waiting until something is ready. And I give some other examples here, like waiting on a web page. You don't have to wait it to load completely until you can interact with it. Really important in games, like you have to be able to concurrently handle things like user input. Otherwise, you would have to skip a few frames of your game to handle the input, and that would give a really jagging and bad gaming experience. And writing a large file could be another example of where you are waiting for the disk to return to you saying, hey, I'm done writing the file. In all of these situations, you could be doing something else. You could be answering to another database call from another request. So it's missed opportunity, really. And I'm going to get deeper into this missed opportunity. So here I mentioned that again, the laundry example where you were the only thread doing work. And notice that at no point there, well, if you consider that you were the thread, we did not introduce parallelism. You were talking about concurrency. Like if you had another washing machine and another dryer, you could think and put the loads at the same time on each of them, then they would be running in parallel. So it's important to really crystallize this difference in your minds, because what we are going to be talking today is mostly concurrency. And it's really easy to mistake this for parallelism. Of course, we also want to reach parallelism because we want to fully utilize all the cores we have on our computers. But async Rust is not it's not the way to do that. Of course, you use async Rust together with other things to get parallelism, like we are going to get into this a bit later, so I'm not going to get ahead of myself. But you have to keep in mind that concurrency is the main point here today, and of async Rust. Okay, here I go again, explaining a little bit more the difference between parallelism and concurrency. So parallel, running at the same time, and for that you have to have more than one core. If you have just one core, you have just one unit of computation. You cannot do two things at the same time, unless you have a logical core which can do somewhat things at the same time, but let's not go into that much detail. Like if you have many cores, you can do things at the same time. But if you have only one core, you can do things concurrently. Like while something is waiting, you can spawn a thread and do something else. And so that's really useful as well. But it's a separate concept. As we talked earlier, it's about interleaving. You can interleave tasks. Okay, so as I said earlier about a single core, we have the situation where you are able to do work concurrently. For instance, you can think of your operating system as doing a lot of concurrent work. Like it's checking your mouse, it's checking your keyboard, it's checking every process running on your computer, giving them each a time slot, let's say, to run for a little bit. And it does this really quickly, so we don't notice that the US is doing all of this work for us. But yeah, it's quickly switching between tasks and seeing if they are able to make progress. And this is the example of a game. So this is a really nice book on WebAssembly and Rust, in which we build this little game in the browser. Uh, and this is it becomes crystal clear that you have to, and the game is built using like it's built from scratch. Like you don't have an engine or anything, so you have to take care of the event loop yourself. You have to make sure you don't block if the user types on the keyboard. So here I'm pressing the up key to jump, and so it's paramount that the frames don't get skipped. Okay, so why asynchronous programming? And here Jon compares with the simplicity of synchronous programming. And there are good reasons for synchronous programming. We're going to explain, to try to make an analogy here. But the basic idea is that most of the time, your computer, your CPU is waiting, either on I/O network or database. So it's or a mouse click or the keyboard. Your computer is idle most of the time. And so this is something that we can really take advantage of. Like while waiting for this other stuff, we can handle, we can use the CPU because it has a lot of unexplored potential that we can leverage. And so that's why we need something like asynchronous programming. And here I want to make this little analogy to understand, to give you a more, how can I say this, a more palpable, a more understanding of how much waiting we really do. So here I mentioned that a modern CPU can do on the order of billion cycles in just 1 second. So in one clock cycle, you could do one instruction. And so this is a measure of how many operations roughly. It doesn't map one to one, but you can imagine that this is how much operations your computer can do in 1 second. And so I take this idea a little further to compare the perception of a computer with the perception of a human, of the 1 human second. Of course, it's also 1 second for the computer, but I make the analogy of what if the 1 clock cycle were a second to a CPU. And so we find that 1 second to us would be equivalent to almost 30 years for a one gigahertz computer. So you can imagine how much waiting is happening here. Like, and I put it on in another way here. I say that when the computer experiences the passing, let's say, of 1 billion cycles, we experience the passing of 1 second. And so this 1 billion cycles, if they were seconds, it would be equivalent to 30 years. And so with this, I bring an example now where, let's imagine we have a really modest web application that receives 16 requests per second. And I mentioned here that a really busy application like Stack Overflow would process 6,000 requests per second. And so let's imagine that for each of these requests, we make a database call. So 16 database calls in total. And each one had half a millisecond to the wait time. And so if we work out the values, we can see that over the course of a month, we've been waiting for 5.7 hours. And if we translate that to cycles, this would mean like 600 millennia in computer time, let's say. And so it's a lot of wasted potential. And that's what asynchronous programming is about, is trying to tap into that potential. But not only that, as I mentioned, the case of games, of browsers, of the operating system, it's not just performance. It's sometimes it's absolutely just necessary for the thing to fulfill its purpose. Like a game needs to be able to handle things in an interleaving manner. Like stop this, check the keyboard, come back to rendering the frame. And so that's crucial to this other point of view as well. And Jon briefly mentions at the beginning that there are use cases where you don't need async, and that's true. Like if you're doing mostly CPU intensive work, I don't know if you are decoding a video or hashing some bytes, some large amount of bytes, like you're going to be doing CPU intensive work from start to finish. If your application is only that, like there's really no point in introducing the complexity of async. But one thing to mention is that in general, async code is not going to run slower than sync code. So it's one of those zero cost abstractions that Rust promises us. I think there are some rough edges where that's not entirely true, but the cost over the course of a long running application is amortized. So in practice, it's as if it's a zero cost abstraction. So it's really nice. So we have to talk about blocking code, and because we are going to see later that one of our goals in using, well, not the goals, but one of the etiquette rules is to not block the thread, because not if you block your future, you have a problem because your executor is running on the same thread that your future is running, and so it means you block the executor. And by blocking the executor, you cannot pull other futures, and you cannot do other work. So we're going to see this in more detail, but the message is don't block the executor. And here I give an example of writing bytes to a file. So what really happens is the operating system is going to queue this operation, this writing operation to disk, is going to effectively park the thread that called it, like stop the thread, go to sleep until I'm done writing, and then I'm going to report back to you, hey, I finished writing. You can continue with your code. And so the OS awakes the thread and it continues executing. So this very sequential code is really easy to reason about. Like if you have any point of waiting, you block and you stop execution until you get a response. This is really easy to reason about, but it's also really inefficient. And as we mentioned a little earlier, we want to avoid that usually. But it's worth mentioning, right, also that a lot of software in the industry, certainly the majority of the software, operates exactly like I described earlier, in a blocking manner, or by using multi-threading, which is kind of an alternative to, is another way to achieve concurrency. So instead of blocking, just blocking and waiting, you can block, but in another thread. You spawn a new thread and then do that operation that you know is going to take a while. This, for a few threads, this is simple, but as you start, as your needs start to change and you start to need more threads, you have more blocking operations, and worse still, if you need to share data between these threads, this quickly becomes a nightmare. And of course, to share data between threads, you're going to have to use the locking primitives that Rust offers. So we're talking about arc, mutex, atomic values, and so this becomes complex really easily. And in many ways, async Rust is simpler, but in other ways, it does more stuff behind the scenes. And so it's not as intuitive as multi-threading. Like with multi-threading, oh, I spawn this thread, and so it's going to do this work, and that's it. Like with async Rust, as we are going to see, there's code being generated behind the scenes. There's new concepts to learn, like pinning, and so things become hard hard to understand in another way. But once you understand, it becomes simpler to use. And that's not true of multi-threading, because once you understand, multi-threading is still is very difficult to use in any real world application. Right. Yeah, channels is another primitive you could use. And I mentioned here a few drawbacks that I covered most of them. I didn't mention the cost of spawning in threads, like they are not free, like they have a performance cost. And that can in part be mitigated with thread pool that is going to reuse. It's again, the cost is going to be amortized because we're going to reuse the threads that you have already spawned. But it's important to realize that if you have let's say 10 blocking operations and you want to achieve concurrency with all the 10 operations, like you don't want to be waiting, you are going to need 10 threads. And so you see that the cost mounts very easily. Okay, so now we start to get into a bit of Rust. The first thing, like Jon starts talking, he starts from a different angle here. Like he starts talking about sync and async interfaces, and then standardization of async interfaces. But what he means here is that the standard library offers certain types that are standard, and so every runtime and executor out there, like Tokyo, Async STD, or small, are going to rely on these same primitives. So this is really nice. And more than that, the libraries built on top of these runtimes are also going to rely on the same primitives. And so it's one point of agreement, and this is really nice. And so we start with this enum called poll, which is what a future returns. And we're going to discuss what a future is, but Jon starts with poll. So a poll can be either two states. It can be ready, or and the value of the resulting value of the future is wrapped in this ready variant, and represented by our T there. I'm going to talk about T also as target, and so I'll use them both interchangeably. And I just wanted to call out here this really nice, not feature of Rust, but of having a type system. Like you can represent complex concepts with types, and this is really nice. Of course, this will depend on how the type is used, but the idea is that we are representing here an operation that is either done, and here's the value, or it's pending, and you will have the values at some point in the future. So this is really key to understanding asynchronous Rust. This poll type returned by a future. Like let me just skip here to the future, and I can go back to the other slide. I just wanted to call out how the poll appears here as a return type, and this is in this wrap type is going to be the return value. So you see that a future is a trait. We use interchangeably here future, the word future, for both the trait and objects or other types that implement this trait. So I may say about a read future that reads from disk, but it's in reality I'm talking about the struct reader that implements the future trait. So just so you know. And so I'll quickly come back to this, but I wanted to mention that where poll appears, so it doesn't just hangs loose there. Okay, so Jon mentions that what happens with this poll enum. So like while it's pending, sorry, let me say that again. Yes, this is better explained in this context. So a future inside the poll method here, it's going to try to do work, and will either return that it's ready with the work, or that it's pending because it's waiting for something to happen. So that's what I mentioned here at the top. So there is an example here where we say, like, let's say we have two methods. Both of them are going to return a future, and one method is going to read from the network, and the other from the user keyboard. I have no idea when the network socket is going to give me an answer. Perhaps it's going to be quick, perhaps not. And the keyboard, like when the user is going to type, like it's totally unpredictable. And we can use these two futures and poll them in a loop, let's say, until they return ready. And so it's a really easy initial way to think about this. Like you go driving futures by calling poll on them. When they return ready, they are done. Otherwise, they still have work to do. And Jon call outs the magic here of not having to worry about threads or any synchronization to achieve concurrency. So you are not going to see in async code, well, in the async samples we have here today, it's not usual for you to see lots of mutexes and arc wrapped in arcs. So because we can achieve concurrency with the async await machinery. Okay, so going back to the trait, there is very little else to say here. Just that the output type is determined here. So when you implement this trait, you, like, let's say your future reads from disk and returns a string. So the type output here would be equal to string, and it would return either pending or ready with a string inside. Okay, so yeah, Jon mentions about standardized polling. This is the same idea of the none here, like every and the future. So instead of, let's say, each library having a bunch of poll methods like poll receive, poll press, instead they can all return a future, and that is kind of the contract that they all have to follow. And it makes it easy to then build things on top of this because they all behave, they all follow the contract of, in this case, the future. Yeah, before going here, I wanted to mention one other thing. To distinguish futures from something like promises in JavaScript land, because Jon uses the word promises, and this can be confusing. And he says the future is kind of a promise, in a way that this is a value that is going to resolve to output when it's done in the future. While a JavaScript, and this is going to happen only if you call poll. And so if you create a future, you don't call poll, and the work is nothing is going to be executed. And we have to contrast this with JavaScript promises, where when you create a promise, like it runs eagerly, like it starts running right away. And so it's important to make the distinction. Like you can think of computation as an object here. And this is, again, a really strong point of having such an advanced type system. Like we can assign this computation to a variable. You can add 5 computations to an array and then run all of them. So that's really strong point of a type system. Okay, and then we move on to talking about ergonomic futures. In comparing how similar async code is to sync code. In general, you can see how comparing the sync version at the bottom and the sync at the top, you can see how the code reads almost the same. And this is really, well, surprising, outstanding, how many adjectives we can use here. Because this is doing a lot more than the sync version, like we are achieving concurrency here. And we are going to talk about what is happening behind. So you are going to see that this code is actually transformed into much larger code. We are about to see that. But this here is just to call out the similarity between the two versions. Okay, I'm going to have to pick up the pace because there's a lot of stuff. Okay, so we're going to look at a handwritten version of this async forward. So you can see what I'm talking about when I say it's a lot of things happening in the background. So this forward, you can think of these awaits as yield points, like the computation could stop here until there is a next value to be read. And it also could stop here until the value is sent. And so these stop points are like two steps of computation. And what Rust does by saying that this function is async and having these await points, so the combination of async await, is to transform this into a state machine that reads more or less like this. This could be step one, this could be step two. But here Jon called waiting for receive, waiting for send. And this is just the beginning, like this is just the type of the state machine, not the state machine itself. And you can see its implementation, part of its implementation here, where we, you can see this has changed. You can see that here we are implementing future for our init forward. And you can see how this is turning into a state machine here with our two states. So here's one state, here another state. And how you switch between states, really important in a state machine, is happening on this line. So you're waiting for send, and then you change at this point to waiting for receive. And if you look at waiting for receive, which is in the next slide, you can see that it changes to waiting for send. And so you can see how the state is changing like a state machine. And all of this is done by the compiler using async await, using only the sync await syntax. So it's really nice that we have this, but it's also, as I said, a source of complexity because well, for many reasons. One, like it's code that we don't see, so it's a bit harder to reason about. We have to imagine, to try to reconstruct what is happening. It's not like with macros where we can say expand this for me and I see the macro expanded. This is actually worse because it's hidden. And we are also going to see that there is an accompanying data structure that is hidden behind it, that is hidden, and that is storing state for this future. And so it's quite a lot to take in. So I won't go into too much detail here. The main idea is the idea of the state machine here that is being done for you. And why, right? Why a state machine? Because this is a way to achieve concurrency. And so you can run this branch. If you are done, you can leave this state. Otherwise, you can change state here and go to the next state. And this is how, and you have to imagine that here we had only 2 await points. We could have many, like I would say 100, but in reality, we can have futures that call futures that themselves call futures and so on. And so you can have really a huge tree of await points. which is going to be turned, each await point is going to be turned into one entry in our state machine. And this branching is going to be much larger. So it's really, really interesting, awesome that all of this is happening and that it works and works well. And it's almost zero cost. It's impressive. Okay. Our original definition of a future, of the future trait, is missing a lot of stuff here. And so Jon has divided this into three steps. One is what I already did, like giving you the idea of a future. The second one, we are going to talk about pin and unpin, and we're going to see that pin is going to enter here. And then we are going to talk about waking up, going to sleep. And for that, we need to talk about wakers, and it's going to be a second argument to this poll function. But just so you have an idea of where we are going. Okay, so this is what I just said. We wanted to demonstrate how much heavy lifting is being done and what it would look like if we had a lot of branches. This is just an aside where Jon mentions that the receiver in that code is very similar to an iterator because it's yielding values until there is no value, and then it's done. And he mentions that at some point in the future, we may get an async iterator. And I mentioned here that it's already on nightly, so you could try that out. And the futures crate has the concept of strings, which is the same idea. Okay, so now I briefly mentioned a hidden data structure that gets generated for us. And so this brings us to generators. So I ask you to imagine here that when we try to send a message through the channel that we have received here, the sender and the receiver, let's assume the channel is full, and a full channel is going to block in the send because we are not able to send, so it blocks until the channel has more space. When we create a channel, we say the capacity that we want, and when we reach the capacity and we try to send more items, the thread blocks. And then we continue with this example saying, like, this is an await point, and so if we proceed, we have to imagine here how polling is working. If we await there and then try to, it's saying here that we are going to need, the idea here is that we are going to need to keep references to variables like our x and tx, so that after when we can resume, we have access to those values, so we can continue. So this is a really important point, and will lead us to the need of pinning. Small spoiler there. So yeah, I talked about most of this stuff. So I want to get a little bit more into this data structure that is generated behind the scenes. So the whole idea of this example was to say that our x and tx, or the thing returned by rx.next, has to be available the next time we try to resume here. Like if we were on a branch here, and we leave this branch by changing state and going to the other branch, we have to be able to access these values that were on the stack again. And so this is why the async keyword and the await points the compiler is going to use them to both generate the state machine and to generate another data structure that captures all of these variables that are on the stack, and somehow stores them in a way that we are able to resume operation and then access those values again. And so this is the key idea here. Yeah, and you would call that yielding, like when you stop execution, make sure you restore your results in this data structure so that you can resume later. I mentioned here it's sort of a smart return, like in the same vein as smart pointers, like you have a return with metadata, like you yield, but you know how to get back to that point. Yeah, here again, same thing. We're going to the sugaring to the sugar this into a loop. So you can imagine here that this has been turned into this, signaling here a generator. And so you can see that the idea is that we are going to loop and call the operation that we were awaiting earlier, and doing the matching on the poll value that we returned explicitly. And so here, if you remember, the future trait returns the enone that has the ready and pending variant. And here we are doing all of that manually. So, so this is why the sugaring example. So we try to read, this returns a future to us. It's either ready or pending. And then we do the same for trying to send a value across the channel. And the same thing happens here. And the important thing to note is this yield, which is not really a keyword. I don't think it's even a compiler keyword, might be, but it's certainly not available to users of Rust. Like, this is not a thing that actually exists. What this yield does is to generate a data structure that I said and store the state there. In a way, like the data structure is, you don't really have to have this final separate step, like saying store this. The data structure is already being used as part of the code rewrite that the compiler does. So you can imagine that Rx here actually reads self.rx, and tx reads like self.tx, like it's already running inside this data structure. But that is all invisible to us. We can only make conjectures about what is happening. Yeah, we mentioned here that it's an internal compiler feature. It's hidden on this data structure. And this idea of a variable that is on the stack is actually a self.a, where self is this hidden data structure. And here Jon makes quite a large comment on the size of generators. Like, if you think about this data structure as having to store the variables, you can see that if you have large variables, it means that you are going to have to store this, of course, as any other variable, you're going to have to store on this hidden data structure. And if you have many of them, and they have larger sizes, you have to be careful about this not being a performance bottleneck, because as futures get resumed and go to sleep and get resumed, or as many things can happen, like they could run on another executor if you're talking about work stealing runtime. So you can imagine that this data can move around. So that's what I'm trying to say. And by moving around means in the end, it means you are doing a lot of man copy operations. And man copies are not free. They are quite costly. And so it's something to be aware. And he mentions here some solutions, like either you can move these allocations, these expensive allocations out of async code, or you can move data to the stack, to the heap, sorry, and just keep a reference on the stack. And this way you can move data around without any issues, because your data is safely stored on the heap, and your reference doesn't change. It always points to the data. So yeah. Okay, so we need to talk about ping now. Let me see how I'm doing with time. Okay. So pin, as I mentioned, we have to keep references to stack variables. But more importantly, there are situations where we have to keep both the variable and a reference to the variable. And when we do this on a struct, let's say, you are effectively making a self-referential data structure, which means that one of its fields refer to another field owned by the struct. And so this is really a hard problem to solve in Rust, because all sorts of issues crop up with that. I'm not going to get into them in detail. What we need to know is that we need to get around this problem. And the way we do this is by using pinning. And so we are going to get into pinning now, and like a large part of this chapter is about pin and unpin. So it's important that we try to understand what is happening. So here Jon gives this other example where we call our earlier function, which returns a future. So this earlier function here returns a future for us, and we try to poll it and return some or return none. This meant that the generator that was generated behind the scenes here was moved. And so in this moving, it had to do all of those allocations, and including variables that references to other variables in the stack, which means the self-referenced fields. And so what this means is that moving, like say you have a reference to a memory location, let's say memory location 3, and you just move the data. So, but your pointer still says that the data is at position 3 in the memory, and so this means that your pointer is no longer valid because your data has moved. And so pin at its core is a way to enforce or to establish a contract that says that your data is not going to move. So if your data is not going to move, it's safe to have a pointer to it. That is the basic idea. And you do pinning like this. No, not like this. These are examples of pinning types. And one thing you notice right away is that you are not pinning the target type itself. You are pinning a pointer to the type. And why are you pinning a pointer to the type? So this is because you don't want the restriction of not being able to move the pin value itself. Like the pin value is okay to move. Like after you wrap in a pin, it's okay to move. But if the pin wrapped the T value directly, it would mean that moving the pin would move the value as well. And moving the value is everything we are trying to avoid. Whereas by contrast, if we move a reference to the value, that's not a problem. Like we are just moving the reference, not the value. The reference is still valid. And so that's why we wrap a reference, not a value. Okay. And here I mentioned that it's not something specific to Rust features or to async await or asynchronous Rust. It's a Rust feature that allows you to use self-referential data structures with any code that you like. Like it's not specific to async Rust. Okay, so I talked about the contract, and the contract is after pinning, I promise that I will not move the type or the data of the type that I'm pinning. That is the contract. And we're going to see some examples of we're going to see the methods implemented by the pin struct, and we're going to see why they respect and enforce this contract. And of course, the prime example is the generator data structure that we talked about. Yeah, and I mentioned that all the methods honor the pin contract. I mentioned already why a reference, not the value itself. And then I'm going to start talking about the methods of the pin struct. So the first one is new unchecked. And you can see that this method is unsafe. And our goal with this method and the others that follow is to understand why they are unsafe, or why they are safe. In some cases, there are safe versions. And so you can see here that after this new unchecked, we return self, which is the pin of a pointer value. We take the pointer and we wrap it in a pin and return self. And if you look at the implementation, you can see that it's really, really simple. It's just calling the struct with the pointer type, but it says unsafe. And it is unsafe because it's a warning. It's kind of a warning or a marker to the user of the library, to the user of the standard library, saying, "Hey, you have to think carefully about this because there are in certain safe invariants here that you, as the user of the call you just made, you have to uphold." And so this is the main idea. Like if this weren't the case, like let me call new unchecked and okay, and I can do anything with the resulting value. It would be extremely misleading because we would then think that it's totally safe. We cannot get undefined behavior, and that's something to be careful about. But you notice that there is a new implementation of pin that is safe. There is no unsafety here. The body of the function also doesn't have an unsafe. And why is that? You can see here at the top that there is this qualifier that is saying that that is restricting the kinds of target values that we can use. And coincidentally, these are the kinds of values that are okay to move. And a value being okay to move is signaled, is flagged, is the way to describe that is to say it implements Unpin, which is effectively just a marker trait. We are going to get and talk a lot more about Unpin, but just so you know, this is why this is perfectly safe. Like if you have Unpin values, it means they are okay with being moved. Like their memory is not going to be invalidated, and so there's no need to impose any restrictions. Um, and if we take a look at get unchecked mute, um, there's a similar thing. Like here, you are returning a mutable reference to the value inside. And so this is complete freedom to you. Like you can take this reference and you can do whatever you want with it, including moving the value. You can do lots of things that and this is one example where you how you could abuse this value. So here you created a pin value, a pin reference to foo. You got a mutable reference to it, and then you replaced it with completely different data. So the ref is safe because all you are returning to the caller is a reference to the target type. And what can you do with the reference? Well, you certainly cannot move the data that is behind this reference unless you use unsafe. So you can with raw pointers, you can move in an unsafe block, you can move whatever this reference points to, but then you are using unsafe, and that's okay. That's what we want. If you want to do something that that has the possibility of causing undefined behavior, you have to wrap it into an unsafe block. And so the goal is achieved here. Anything that you want to do unsafely, you have to wrap it unsafe. Okay, and then we talk about unpin. And then unpin is, as I said, flagging that something is okay to move. And one interesting here is that unpin is not exactly an auto trait. Like it's not a blanket, not a blanket. It's not an auto trait like other things like copy, for instance. If every not copy. It escapes me a good example of an auto trait, like send and sync, for instance. Here, it's not the case that if every field, it is the case that it's going to be implemented for all types, but this is something done by the compiler. It's not something that right now you could do yourself. Like you cannot. Actually, the opposite is true. Like you cannot implement the negative of unpin. We're going to get there. But the basic idea here is that unpin types and the compiler defines this with its own machinery, that if you have a type and all of its fields are unpinned, then the type is unpinned as well, which means the type can be moved without any issue. Okay, so what is an example of a type that can always be unpinned? Let me see if I have an example here now. A box, for instance, if you box a type, any type, it means you have a reference to something that has moved to the heap. And so this box is always safe to assume that it is unpinned. It's safe to move. Like safe to move means the data that it references is not going to be invalid, or the reference is going to always be valid. Other example is types that don't have references to itself. Like if you don't have the references, why would you care about data moving from one part of the code to the other? There's no reason. So here's what the compiler does for you. It implements unpin for all your types, as long as their fields are also unpin. And when we want to construct, like if you have a self-referential data structure, like you have what? You have a field and a raw pointer to that field, let's say. Rust doesn't know that pointer is pointing to to the field of your particular struct. That pointer could be pointing to anything. And so it's our job, or in this case, the compiler's job, to say, hey, this is actually not unpin. And this starts to get a bit confusing because we are negating the negative. But the idea is to say that, no, it's not okay to move the underlying data. And here I mentioned that you cannot use the syntax. What you can do is to add a field to your struct that the field itself is not unpinned. And so by consequence, your type is not going to be unpinned as well. And so this is going to achieve this effect, as if you had said not unpin. Yeah, the compiler can do this. You as a user cannot. And so the compiler has done this for phantom pin, and that's why we use it here. Okay. We talked about the pin contract. Like once you pin something, you can no longer move that in memory. The value pointed to by the pin. What else? Okay, here we mentioned as well that something being unpinned by default is a really good ergonomics win, because otherwise, if you were to, every time you had to poll your future, you would have to use unsafe code. Because remember, pinning a self-referential data structure requires calling new unchecked, and new unchecked is unsafe. So every time you would have to have an unsafe block like this one. So this is not nice because all of a sudden, if you want to do async, you are sprinkling your code base with unsafe code. Luckily, two reasons, two things. One, this happens behind the scenes. Like we don't usually. This is going to be Tokyo's or small or async STD's problem. We don't usually, like not often, we don't pull our futures manually often this way. This is one thing. The other thing is, since Unpin is implemented for almost everything except self-referential data structures, it means we can call just ping new without the unsafe most of the time, even if we had to do this. So that is nice. That's ergonomics right there. Okay, I already mentioned about pinning to the heap. Why box_t is always safe to move. So you can implement a pin for it, regardless of what t represents. Okay, so this is one way to pin to the heap, moving to a box and then pinning. This is pinning to the heap. Box even has this method, I don't know what it is, called pin. So we have box pin, where you can do the boxing and the pinning with one call. But something else you can do is pinning to the stack if you don't want to pin to the heap. And this is how you do it safely. So you have some type foo, and you want to pin it. So you have to keep the variable on the stack. It is on the stack. You don't have to do anything special. But if you shadow, the recommendation is to shadow this variable by using the same name and then pinning it. So now you have the variable foo on the stack, but it's no longer accessible to you. What is accessible to you is the pinned foo. And so this is one way to ensure safety. There is a pin_utils crate, which has a macro that basically does these two statements for you, just so you don't have to write unsafe yourself. Of course, if you could name here foo1, foo2, And if you didn't move full one, that would be okay too. But of course, we don't want to introduce this possible situations where, I don't know, a different developer could come a month later and full one was defined way at the top, and now the relationship to full two is not clear, and so he could try to move full one. So it's always nice to prevent or to disallow invalid states, like the old make invalid states unrepresentable, sort of the idea here. Um, and why pinning to the stack? Like, it's very useful when you are in a no std environment where you cannot rely on a heap. Okay, so here was just introducing again, showing how pin is called with unsafe. So nothing too much new there. And now we are going to start talking about another big part of Async Rust. So just to recap, we talked about all the introductory material, multi-threading, synchronicity, asynchronicity. And then we talked about some of the standard types that exist, like future, the value returned by a future, the the future trait that generates futures, and all the machinery behind async await, generate a state machine, and also there is a hidden data structure that holds on to our data, so we can resume after pausing, and be able to work with the data again. And now we are going to talk about actually the part of the code responsible for executing these futures, for driving them to completion, and also about going to sleep and being waken up and registering for waking up. So this is where we are headed now. So we say here that the piece of code that does this, running our futures or instructing our futures to run, is the executor. I mentioned that we don't usually call poll manually because that is done by an executor. And this is basically how it works. Well, a simplified version of an executor could be just a loop where it goes through a list of futures, looping over them and checking, are you ready? If you are done. Next future. If you're pending, go back to the queue, and I'll keep looking other futures. But this is really expensive, of course, because let's say all futures are busy, and so you would queue a CPU core just to keep it looking at every future, saying, are you ready? Are you ready? You are not. You are not. And so obviously we need something smarter. And so there is a whole waking mechanism entirely dedicated to not, well, to doing just that, to reacting to events that then wake up is kind of a misnomer. We're going to talk about this. But let's say to wake up the executor, saying, hey, pull these features because they have work to do. Which is obviously much more efficient to work on this event basis. We don't waste CPU cycles. Examples of when to wake up, like a network packet has arrived, the mouse has moved, the timer is completed, the data has been sent on this channel, the data has been received from this channel, there has been a hardware interrupt. And so there are many events that could cause a wake up. And so finally, we have the actual definition of the poll method of the future trait, which includes this second argument, which is called the context. And the only important thing here for out of the context that we want to look at is the waker. So this returns a struct called waker that is part of the standard library as well, which is going to offer you a method called wake. And here there is an implicit contract here, which you could call the poll contract, which is if a future returns pending, it has to arrange itself to call waker.wake at some when it's ready to do more work. So it's the future's job to do that. And the executor's job is to pass this waker to the future. So the executor is going to call poll, and they have created the waker beforehand, and they are going to pass this here together with the context. So that's basically the mechanics there. And the executor actually determines the entire behavior of the wake call. Like the only thing left for the future to do is to arrange for the wake to be called, but it takes no arguments. It has no configuration, like just has to be called at some point when there is more work to do. I already mentioned the poll contract. So like I said, poll pending means you have to arrange for wake to be called. And here I make the distinction between two kinds of futures. They're all the same. They all implement the future trait, but this is a real point of confusion if you are not aware of them, because there are leaf futures, which are futures that are actually going to interact with an event source. And there are other futures that are just call other futures, maybe including leaf futures, maybe non-leaf futures as well. But these other outer futures, they don't have to do nearly as much work. Like if they call a leaf future and the leaf future returns pending, they can just return pending themselves. Like they don't have to arrange for something to be called on for the wake method to be called, because this arranging has already been done by the leaf future. And so if you are not aware of this, like it can become really confusing, because we are going to say, well, but where this is happening? Like I don't see a hardware interrupt. I don't see a communication within, for example, I don't see any registering of events so that I can be notified at some point. It's all behind the scenes. But in a leaf future, you have to arrange for the wake to be called, and so it's quite different. And Jon divides leaf futures here in two kinds. Ones that can run in a process, like a regular channel is one example. And out of process is something that depends on something that is external to our process, like reading a TCP packet, interacting with reading from disk. We need some external, usually AOS primitive to which we communicate, we register interest, and we receive notifications saying, hey, I'm ready to do something. And so this is quite challenging. And this is something that we usually also don't interact directly. And so all of these hidden bits, they you can see that they add up to hide. It is a good thing in the sense that pragmatically, like day to day, we wouldn't want to have to worry about this stuff, but it makes it difficult to understand everything that is happening behind the scenes. Okay, I'm going to skip this part because I've just mentioned it. And here I'll briefly mention the different abstractions over this ways to handle events. Like every operating system has a different way to do this. Like Linux uses EPO and Mac uses KQ, and they operate on a similar way. And Windows operates on a different way, but it's the same idea, like reacting to events, registering to events. And Tokyo depends on the Mayo crate, and the Mayo crate abstracts over these three things. So here's a sketch of out of process waking. So yeah, the executor is going to keep track of all the event sources. It needs to listen. And again, the future is going to arrange for the wake to be called. And so it means it's going to register with this event source. And when the executor cannot make progress, it's going to go to sleep. No future has work to do, I'm going to sleep. And this is where the waking up idea comes from. Like if there is an event, then I'm going to wake up the executor again. So this whole registering of events is done by the reactor. We give different names here, but we could perfectly implement the reactor as part of the executor. It's just nice to give different names to different parts of the executor. I think in practice they are implemented as one thing. I think for performance reasons, I think Jon mentions that. This tight coupling with leaf features. Remember, leaf features are the ones that have to be able to arrange for the way for wake to be called. And so they have this tight integration means there is this problem of compatibility with different executors. Like if you wanted to use a different executor, this can be a pain. I mentioned before the waking as a misnomer, and I can quickly explain why that is the case. So you are not always waking. Like you can imagine what wake does is say, hey, this future is ready to do work again. So executor, when you start polling again over all the futures, look at this one. In actual code, this would be, I'm going to put this future in a ready queue. And this ready queue is the one going to be iterated by the executor. So the executor could actually be busy doing work and wake being called, which means another future is going to be added to the queue. But the executor was never asleep. If there were no more futures to make progress on, then the executor would be asleep, and the wake call would not directly wake the executor, but rather put a pull on the queue, and that would wake the executor. So it's an indirect effect, and can be a source of confusion as well. If you have the mental model of, hey, I have to wake the executor, that's not true. Yeah, why the executor needs to know which filters to pull. Yeah, we kind of covered this with the whole idea of registering for events, and then when that event happens, you go back to the future, and the future says calls wake, meaning the future is ready to do more work. And this whole process avoids the need to keep polling, writing a busy loop to poll indefinitely without stopping. So as I mentioned before, you can see that that we construct a tree of futures. So a future can have an inner future, which can have more futures. And at the end of the tree, you have the leaf futures, as we discussed. And the one thing to note to call out here is the concept of a task. A task would be the root node of this tree. it's the actual future that we send to the executor. And so this is another source of confusion because you could write the single future altogether. Um, and if you want something that you also want besides concurrency is parallelism. And if you want parallelism, you have to have two futures, two separate futures, two separate root futures to run. And so this is something to be careful, like as careful in the sense, make sure you don't fall into the trap of thinking that every future is running in parallel. Only root futures can be run in parallel because everything else inside a future is just code. Like the future doesn't know that it's composed of inner futures. It doesn't have an idea. It's all that machine state machine transformation that we talked about that is happening behind the scenes that it doesn't really know, doesn't have this knowledge of the inner code. Yeah, Jon mentions the idea of a sub executor to bring up this topic of root futures. And this enters in a lot of detail of having a sub executor, which is kind of what this select does here. So it either runs this future or this future, whichever finishes first. So blocking in async code, I covered this at the beginning, like don't block. And Jon provides this rule of thumb of 1 millisecond, like don't block for longer than 1 millisecond. If you want to block, you have options, which in the case of Tokyo is spawn blocking, which basically means it's going to give you a dedicated thread to run your expensive or long-running computation. And then there is a server example here where we read connections from a socket, and for each connection we await on this future. We can see that this code is actually synchronous. Like you are stopping here. You are handling one request at a synchronous in the sense that if you don't have anything else running, if you have more code, of course. On this await point, you could execute this other code. But in this context, you are running one request at a time, handling one request at a time. And this is really bad. Like you don't want to have a server that runs one request at a time. What we want is to do something like this, where we use Tokyo spawn to create this future as a root future. And remember, root futures we can run in parallel. And so this is going to accept, let's say 10 connections, and it's going to spawn these 10 futures, and all of them are going to run in parallel. If you have 10 cores, of course. So you can see in parallel and concurrently, like this handle client, imagine it has 10 await points as well. So you can imagine that if you hit one await point, I can make progress with another future. That is the job of the executor. Yeah, it's similar to spawning a thread. Okay, for the reading, so you have the Rustaceans book. I would recommend starting there. There are some really nice blog posts about faster than Lime. Especially this one, Unpin and suffering is really well explained without introducing too much complexity. The Tokyo book, the Tokyo documentation is phenomenal, really worth reading it. Jon's videos are really good as well. I recommend starting with the longer one. He recorded this video before async await was stabilized, so you might feel like that is not super applicable, but it is. Everything he says is really helpful to create the mental model to understand everything. And his shorter video, he tries to do something more applied and doesn't go into the details too much. So I would leave it as a second, so because it could cause confusion. The Async await RFC has a lot of history there. Is a nice read as well. And then Without Boats compiled, not super recently, the whole Async story in Rust. I recommend this other really good book called Asynchronous Programming in Rust by Carl Frederick Sampson. Really nice. It uses how many pages? Let me see. It uses 300 pages to do what John did in 20. So you can imagine it is a lot more detailed, and it's able to go more deeply and explain things more calmly. Yeah, and external library and documentation of crates, great source of knowledge. That's it. I'm sorry I spent so much time. Do we have questions?
Thanks, Diogo. Thank you very much. One of the questions on the talk is, can we get a copy of the slides? There's a lot
Sure,
of
of
links
course.
on there.
Yeah. I don't know how, Kira, how do we distribute this, but I think we can arrange that, right?
I'll talk to Kira about it.
Okay. I
We
forget you are
usually put a
organizer
lot
as
of
well.
links. We usually put a
Sorry.
lot of links on the description in the YouTube video.
Yeah. Awesome.
Any questions?
I have no idea how many people. Okay, 12 people are listening. I need some water.
I don't think there's any questions. Okay, that was great.
I have a question.
Oh, go on.
Sure.
Yeah,
Should.
just to clarify, did you say that a task could consist of multiple executors running in parallel?
No. An executor can run multiple tasks. Well, not really. Tokyo can spawn these multiple tasks and use one executor for each, let's say, and so you get parallelism. The executor's job is to do concurrency, not parallelism.
Okay, so the executor would be running in multiple threads, the same executor.
Yeah.
No.
I think a separate executor.
So what it would do is that each thread from the thread pool that Tokyo controls will have a bit of code that's responsible for tapping into I imagine shared data about what futures are ready to be polled again.
Yeah.
So it's kind of work stealing.
Okay, so it's a common list of tasks that multiple threads work against
In Tokyo.
in Tokyo.
Right? Your executor that can implement and poll futures doesn't have to work with threads. It can all run on a single thread, right?
Right.
It's about concurrency. Yeah.
It's not a constraint on the actual async await mechanism.
No, I understand. Yeah. I guess a single-threaded task is like a time sharing in the old days on one CPU.
Yeah, adding on to that, like you can think like let's say you have 5 executors running, and they each have their lists of tasks that they are going to be polling, like independent of each other. And let's say one executor gets really busy, and the others are not so busy. And that is where the work stealing can happen. Like one executor can say, hey, I'm going to steal this task for a little bit. I'm going to run it. And when I'm done with it, I'm going to send it back to you. So I have to send back to your queue, but I can run it on mine, on my loop. So this is possible too. This is the work stealing that is done by Tokyo. Tokyo's runtime. I didn't talk too much about runtime, but yeah.
Thank you. Great talk.
Yeah, very good talk. It's really difficult to talk about pin and wake,
especially in so little time.
Yeah, one of the ideas I've been having on a single thread based executor is like a frame based executor for doing video games, where you can have code that does some work and then it waits and then it will continue on the next frame. So you then poll everything at the beginning of each frame. I'm not sure if that's useful or not, but it's an idea I'd be having, something I would like to try to implement.
Yeah, you are into game development, right?
I am a game developer.
You are a game developer.
Yes.
Cool. Awesome.
And my bread and butter. Any other questions?
Remember the Pacman rule. Like, feel free to ask questions, even if you're new. Like, I saw that there was a lot of new participants today.
It's great.
Like first timers. If you have questions, please do ask.
Going once. Going twice. Okay, let's wrap things up. Again, Diogo, thank you so much for tackling this really difficult subject. You explained it really clearly. I recommend people do pick up Jon's book yourself, and give it a good read. Kira's posted some dates on the next talks for the next coming chapters. If I could find them. Yes, so chapter 9 will be on the 3rd of July. If Zoom will stop moving the chat window. I've lost it again now. Chapter 10 on 17th of July from Vladimir, and we're still looking for people to do chapters 12 and 13. So if you're up for reading those chapters in the book, please let us know through the Discord channel. And thank you so much, everyone. And thank you, Diogo.
Thank you so much for coming. You too. See you guys.
Bye-bye.
Bye-bye.